Algebra 2, Chapter 10, Section 2, Working with the Base of an Exponential Expression. Growth factors are often expressed not as factors but as rates, usually in percentage form. You hear about this all the time when someone says, my interest, my bank account, is 2%, or my return rate in my stock portfolio is 8%. Okay? They're not talking about a factor, they're talking about a growth percentage. Remember percent, which comes from Latin per hundred, is just another way of writing a fraction where we divide by 100. So 2% is another way of saying 2 100ths. 8% is another way of saying 8 100ths. Now that may seem really dumb and trivial for 2 and 8%, but what if I ask you what 327% is? That may seem very counterintuitive. Just write 327 over 100, okay, which is 3.27. Or I might ask you, what is negative 75%? That'd be negative 75 over 100. Or negative 2,342%. That would be negative 2,342 over 100, which is negative 23.42. So that can help with very kind of non-intuitive percentages. Just remember, it's just that number over 100. The growth factor b is related to the growth rate with this very simple equation. 1 plus the rate equals the factor. Okay, so a rate means I grow by 8%. I don't multiply by 8%, I multiply by 1 plus 8%. Okay, so if I grew by 9%, then I multiply my factor I'm multiplying by each time is 1 plus 900ths, or 1.09. And while we're talking about percent, I want to mention there's also, you might notice as you're doing your work in the future, instead of a percent, you might notice someone talking about growth or other numbers in ppm, which stands for parts per million. So if I said the colony of bacteria is growing 70 ppm a second, then that would mean 70 parts per million, 70 over 1 million. Instead of a percentage, I gave it as a parts per million. Okay, so it's a very small growth. I don't know if we see this in the homework in our class, but you'll see it at some point in science or some other field. You invest $500 in an account earning 10% interest every year, which is an amazing return, by the way. Find the value of your investment after 10 years and t years. So A, my value is going to be the initial amount I deposit times some factor b. Well, the factor b is 1 plus the rate. The rate is 10%, 10 per 100, which is 0.1. So b would be 1 plus 0.1, which is 1.1. So I multiply by 1.1 to the t for each year. Okay? Sorry, that's the answer to part b, which maybe is helpful to do first. So the part A, the answer would be 1.1 to the 10th power. To multiply by 1.1 10 times. And this is where a calculator is going to be very handy in this lesson. So 1.1 to the 10th power is 2.593 some on. Multiply by our $500 that we start with, and we get 1,296 and 87 cents. So our value would be 1,296 and 87 cents. Okay. We could just write this as money. So after 10 years, our balance is that. After, let's finalize our answer to B. After t years, our balance will be $500 times 1.1 to the whatever number of years it's been, t. State the growth rate r and the growth factor b for each of the following quantities. So A, the size of the population grows by, and here's again a good example of why want to remember per 100. 0.22% each year. So 0.22% is 2.22 over 100. That's our rate, R, which as a decimal, we could shift the decimal place to the left twice when we divide by 100. 0.0022 is our growth rate. So R is 0.0022. It's the first part of our answer. And then the growth factor B is just 1 plus R, which would be 1.0022. You need to be very careful, by the way, with growth factors with rounding. You do not want to over-round growth factors when there's a bunch of zeros here, because if you subtract the 1 after over-rounding, you will get the wrong answer. So take care with rounding and growth factors. So part B, the value of an investment grows 11.4% each year. So our rate is 11.4%, which equals 0.114. So our growth factor B is 1 plus the rate, which will be 1.114. Part C, the area of a lake decreases by 7.4% each year. Okay, so our growth rate, remember this is growth rate, not decay rate. So here in English we've given a decay rate. It's decreasing 7.4% each year. In other words, if the area was 100 when we start, after 1 year we could subtract 0.074 times 100 to get our decay. Okay, so the way we can deal with this is R is not a decay rate, it's a growth rate. So R, the growth rate, will be the negative of this decay rate, negative 0.074. So whenever you have decay, your growth rate will be negative. And your growth factor is 1 plus R. 1 plus negative 0.074 is 1 minus 0.074, which is 0.926. So when we have decay, we have a B less than 1 and an R less than 0. So for decay, the rate needs to be negative and B should be less than 1. For growth, the rate has to be bigger than 0 and the factor bigger than 1. Here we have a typo. What is the growth or decay rate R of the following exponential functions? Now here we can specify a decay rate, but we need to write it out, which we have, because if we just write R, it's confusing. So we'll write it in English. Here we have a B of 1.041. So remember here B is 1 plus R. 1 plus R. So we have 1.041 is 1 plus R. So our R is 1.041 minus 1, which is 0.041. And writing that in terms of a percentage rate, this is how we would normally say it in English. We'd have a growth rate of 4.1%. Moving a decimal back to the right twice, so that we could divide by 100, multiply by 100 to get the percent. That was A. Part B. Here we have a B of less than 1, so we should end up with a decay. So we have 0.992 is 1 plus R. So we subtract 1 and we get negative 0.008 is R. Now, in English, we're not going to say the growth rate is negative 0.8%. We're going to say there was a decay rate of positive 0.8%. Okay, so if we have a negative growth rate, we're going to say in English a decay rate and make it positive. The growth rate is the negative of the decay rate. C, here we have the square root of 5. So what's the square root of 5? We need to go approximate this. Square root of 5 is 2.236 roughly. Remember, we don't want to overround. 2.236 should be enough for this problem. So B is 2.236. So our rate R would be, and we can rewrite this equation, by the way, as B minus 1 is R. So if we just subtract 1 from our B, we get 1.236. Okay, and we can just write, we have a growth rate of 1.236, or we can write it as a percentage, 123.6%. So 100% growth would be doubling, because you'd have 1 plus 1 is 2. Are the following functions exponential? This is an example from the previous slide deck. We don't need to do this. Find the growth rate R and the growth factor B of a quantity, sorry for the typos, guys, quantity that A doubles each year, and so on. So A, if we're doubling each year, that means we're multiplying by a factor of 2. So B is 2. And remember that rate is simply B minus 1, so our rate would be 1, or 100%. B, here we have a rate of 200%, which is 200 over 100, or 2. Remember, 1 plus the rate is the factor, so the factor is 3. We're actually tripling in this case every year. And C, we're having, our growth is halving, which means we're actually decaying. Okay, and so our factor would be 1/2 that we're multiplying by, which would make our growth rate, remember it says find the growth rate, so it should be negative. It should be 1/2 minus 1, which is negative 1/2, which we could also write as negative 50% growth. Which again is confusing. In English we would say 50% decay, or I got 50% off, meaning decay of a price, for instance. Now let's look at a table of data and see if we can figure out if this is an exponential function. So the technique for finding out if data is representing an exponential function is to see if the data is growing by a constant rate. I'm sorry, that's linear. See if it's growing by a constant factor. So are we multiplying the output by the same amount each same step of the input? So here we fortunately have the input in growing by 1 at each time. So we have the input spaced evenly. So if the output, if each output is a constant factor times the previous output, then we would have exponential growth. So if 4.4 is some constant b times 4, and 4.84 is some constant b times 4.4, and so on, then we have exponential growth. So if we think about each of these equations, the constant b would be the ratio of the second output to the first. If that ratio is constant, then we have exponential growth. So if we write down the ratio of y at x is 1 to y at x is 0, we would have, again, 4.4 over 4, which is 1.1. And here you have 4.84 over 4.4. Getting a calculator. 4.84 over 4.4 is 1.1. And what about the last pair of points? 5.324 over 4.84. Is that also 1.1? 5.324 over 4.84 is also 1.1. Since the growth factor is constant between each pair of points, we have exponential growth. So the answer is yes. And our A is 4, because that's what the initial value is of the exponential function. And the B, the growth factor, is 1.1. So the answer is yes. A is 4, B is 1.1.